This is Euclid Book 3, proposition number 36, and we are only just 2 proofs away from finishing Book 3, and we're going to take this very quickly here. We have a circle. It starts at point A here, comes over here to point B, goes over here to point C, and comes back over here to point A. Now Euclid wants you to take some random point at D. We're not going to take a random point here because of what is required of this point D. First of all, Euclid wants you to draw a line from point A through the center of the circle, which is at point F, through point C, which is another point on the circumference of the circle, all the way down to point D. Now this wouldn't be so bad, except that point D has to then be joined up with point B, which is another point on the circumference of the circle. This is a tangent line, okay? This line from D to B, if extended out, would be a tangent line. If you don't know what I'm talking about, you need to go back to Euclid, well, to the video I have on tangent lines, okay? I do have a video on tangent lines. You need to go back to it, then come back here. All right. We have already said that line DCA cuts circle ABC, and line DB, or BD here, touches circle ABC. This is a tangent line here. We have found that F is the center of the circle. How do we do this? You can use Euclid Book 3, Proposition 1 to find it. Doesn't matter. All right. Then we join points F and B here together. There's a line between points F and B. All right. Now, we have an angle called FBD, and it is a right angle. How do we know this? Because of Euclid Book 3, proposition number 18. Now, how do we know that line AC here has been bisected at F? Well, we know that when you have a line that starts from the center of the circle to the outermost edge, that's a radii of a circle. And FA is a radii of a circle, and FC here is a radii of a circle, and they are exactly the same length because all radii of a circle are equal. Therefore, line AC has been bisected at point F. Now, we're going to add the length of AC here and CD, okay? The length of AC and CD. When we do, we get line AD. We're then going to use the length of AD to form 2 sides of a 4-sided rectangle, okay? And then we're going to use the length of DC to form the other 2 sides of that rectangle. So you're going to have a rectangle, 2 sides of which are going to be the length of AD, and the other 2 sides are going to be the length of DC. Okay. Then we have an area within the rectangle we just formed. And we talked about this in great length in the last video. Remember Euclid Book 3, Proposition 35? If you don't, you need to go back. Anyway, and of course we already talked about all this in Euclid Book 2. But if you have any more questions, you can leave me a comment, whatever. Point is, we have formed a rectangle with the length of AD and the width of DC. The area within that rectangle, if it were to be added to the area in the square of FC, well, where's FC? Well, here's F and here's C right here. So FC becomes one side of a 4-sided square. Okay, so each side of this 4-sided square would be the length of FC. And the area in that square plus the area within the rectangle ADDC would equal the area of the square of FD. Well, where's FD? Well, here, F starts here, D over here. So you'd have a 4-sided square, and each one of the 4 sides of that square would be the length of FD. And this is by Euclid Book 2, proposition number 6. Now, the length of FC here is exactly the same length as the length of FB here. Okay? And how do we know this? Because all radii of a circle are equal. Therefore, we can say that the rectangle formed by the sides ADDC, which we talked about a minute ago, plus the square of FB. Where's FB? FB is right here. So we're going to form a four-sided square, and each one of the sides is going to be the length of FB. If we add the rectangle ADDC plus the square FB, those two areas together, we would get the area of FD. Well, where's FD? FD right here. You would form a square, and each one of the sides of that square would be the length of FD. Okay. Now, the square of FB plus the square of BD equals the square of FD. Okay, let's find all these little letters. FB is here, so you take the length of FB and you form a four-sided square, and when you form that four-sided square, each one of the sides of that square would be the length of FB. You'd find BD. BD is right here. Alright, you'd form a square, and each side of that square would be the length of BD. The four sides of the square of BD would be the length of BD. Alright, so the area in the square here and the area in the square here would equal the area of the square of FD. Well, here's F and here's D. You would form a square, and each side of those squares would be the length of FD. Alright, and we can prove this by Euclid Book 1, proposition number 47. Therefore, the rectangle formed by the lines AD and DC. Well, here's AD and DC right here. Okay, the rectangle formed by those two lines, and the square formed by FB. Well, here's FB here, and we make a four-sided square. Each side would be the length of FB. Those two areas together would equal the area of FB. Of course, we'd have a square of FB, and each side of that square would be the length of FB, plus the area contained by the square of BD. Well, here's BD here, and the area inside of that square. This square plus this square would equal the area of rectangle AD plus DC plus the area of FB. Alright. Then if you remove the area FB from both sides of that equation, you get the area of the rectangle ADDC equaling the area of square BD. Okay? And that's what Euclid wanted you to prove. Now this is part one of this two-part proof. I will show you more in the other part of the proof. I want you to stay tuned.